Okay, hello guys.
Hi, Dada.
Hello. Today's numbers and names number 13, and we will talk about free, beautiful, and dangerous universe. Ours and maybe somebody's else. Okay, you said that you answered my questions for the previous inventions. So, what kind of inventions did you make?
For Visa.
Just one after another. Okay.
So we did it for the windshield wiper. I thought instead of spraying up soap and then wiping it, we could put a vacuum on the windshield razors that swish around on it, a vacuum on it so it sucks up all the dirt.
Ah, that's a good idea. A vacuum. And how do you put this vacuum, by the way?
I would attach it to it and make a wire going from there onto the top of your car, and then sort of into the wall of your window.
But still the wiper will go because the wire, right? So the vacuum, like anything other idea maybe?
There's three wires. One turns it off, one turns it on, and then the other one sends the dirt into a bucket in the back.
What about some other idea for the wipers?
So, there's one idea that was Papa's one. So my idea was that you can put, you know how windshields, you spray water to clean it?
Okay.
Instead of that, you can put like a tube at the top, like a smaller or something, and make strong wind come out so it blows away all the dirt.
Oh, okay. So good idea. Yeah. So anti-vacuum, right? This is vacuum, and this is anti-idea for the vacuum, right? Okay, good. Good.
That's the opposite.
Okay.
Take the opposite.
And Papa's and
Uh-huh.
Papa had his own idea where you can make the windshield vibrate, but you won't. But it vibrates so fast you won't be able to see it. It just makes, and then when you vibrate, it makes all the dirt go away.
What about vibrating the whole window? Why wipers?
That's what we're doing.
Yeah. All right.
Yeah, that's what Papa said.
Yeah. Also you can make actually small holes in the window itself, right? They're so small that you cannot really see them, and they can use as a vacuum. Just use vacuum, but without the wipers. You know, the windshield will be the vacuum itself.
Hey, Dad.
Uh-huh.
I have a good idea for a washing machine.
Okay.
So you sort of have little tubes. You fill them up with water. You attach them to all parts of the clothes, and then you have this electronic device. You turn on, and then it squirts it all into it. So it's sort of pretty wet, and then you can hang it faster.
Yeah, but with Papa, but because the thing with Papa's is that it's more. Papa's is more.
I didn't get the idea. Electronic what?
Never.
Okay, so Papa had his own idea also. I couldn't think of one because Beats and Papa basically took everything.
Yeah.
Mm-hmm.
Papa's idea was that you can have like a hose, and with except the end of the hose is stopped, like blocked, and then there's gonna be little holes in the hose.
Mm-hmm.
And there could be multiple strands of hoses coming off the main one.
Mm-hmm.
And you can put a pen inside them. And when it starts spraying, it sprays inside and also the outside.
But again, the hose, right?
Huh?
Can we go without the hose?
Why?
Any idea?
Just put it under the tap. I also have another idea.
No, just first.
You can put it.
Can we go without the hose, and then the idea later, okay?
I have another idea for a washing machine. You can put it inside the
Can we finish the first idea first? Can we think about? I'll listen to this a little later. Just in a sec. Just any idea maybe? Can we go without the hose? Continuing this idea, your idea of Katya's, right? It's Katya's of the washing machine. Or whose? Papa's? Can we go without the hose there?
I don't think so.
You don't? Huh?
No, come.
Do you know what your clothes are made of mostly today? Some of them are natural, but most of them are not.
So
polyester, whatever. Lots of plastic, right? Also different type of synthetic materials, right? So, any further idea what we can do without the hose? It's still threads, right, guys? Still threads. In many materials, even synthetic, there are threads. Can a thread be actually air tube
Yeah.
for the vacuum?
Yeah.
So we can use these threads, and then probably the clothes will wash themselves, right? With this vacuum, and spray too if you want. So you can use both. That's just a small thing.
The best idea, Jen.
Huh?
The best idea for the washing machine we had was take the garbage bag, put whatever you need to wash in there, with soap, and just give it to the kids and tell them to play
Football.
Someone in the middle.
Yeah, good idea too. Yeah, why not?
It's my other idea. So look.
Okay.
So there's tubes and holes in it, the same structure, except it doesn't spin.
Okay, guys, good. Okay, you said something, some new idea. What was that?
I'm still continuing my new washing machine one, and then you put the detergent in the holes. They will spray it onto it, and then holes will get the ones that didn't get into the holes, and then they'll get it back into the tube and spray it back.
Okay, good. Okay, now let's finish with this. Good, nice, guys, great inventors. Now a new type of flying. Okay, you didn't get any idea. I can suggest at least for you to think something, right? So many years ago there was the idea that I actually calculated this. So you know that there are clouds, right?
Yeah.
And you know that clouds are pretty heavy. You know that like a thunderstorm cloud can weigh hundreds and even thousands of tons of water. That's very huge, right? Lots of really, and they are flying actually. Okay, so what we can do, we can use these small particles. They're small particles called aerosols, right? And they are flying by themselves. They're actually falling, but they're falling very slowly. And if you can manage to hold on them, so you create the cloud, artificial cloud of aerosols, right? And then you hold them. There is a way how to do it actually, like by electrostatic. You know, use them like you know the balloons that you go and it's glued to the ceiling, right? When it's electrified. Remember?
Yeah.
So the same thing. These small things, aerosol particles, they can be electrified, and then you can put like a light electrical grid, and it will not push all of them down. You know, so you can fly on the cloud like you fly on the big balloon. So that's the new type of flying. You can invent many more. I know. Just think about it, okay? Okay. So we'll finish with this. Now we'll start our new thing, right? Okay. There's a fine, beautiful song which your papa loves. Прекрасное далеко, не будь ко мне жестоко.
Oh yeah. Yep. That's
Right.
also my favorite.
Okay. So let's talk about our universe a little and math in it. Okay, just say. Okay. We have our universe, right? Like for example, big one, right? All of our universe, all the features, everything that we see, not see, whatever. And there are lots of laws and everything, mathematical axiom, which actually restricts behavior in this universe. You probably understand already now that axioms are restrictions, right? Restrictions. Like for example, like commutativity axiom, right? It's A by B equals B by A, right? Or in other case, maybe other operation. This is maybe like multiplication, right? A plus B equals B plus A. Commutativity, so we can change the positions, right?
But
Yes.
A minus B doesn't equal B minus A.
Exactly. So if we have I, means that's a good thing. It's not equal B minus A. Actually, it equals, but it equals what? Minus B minus A, right? So this is called because this is minus, appears minus, it's called anti-commutativity. The same thing, by the way, with the division. A divided by B, right? It's not equal B divided by A. Right?
It's different.
But what is equal? It's equal to
Inverse.
Yes, inverse. -1, right? Inverse.
Good, Lisa.
So anyway, this way, that way, this is, I don't know what's the name of this, but this is sort of anti-commutativity but for multiplication. So the other like good, well-known like axiom is associativity. Association, so associativity, right? It's thing like this. If you A by B, right, do first and then by C, right? It equals, if we do that, B by C, then first and then A by BC.
That's not
Associativity.
that's not associativity.
What is it then?
I don't know what this one's called. Associativity is when A equals B and B equals C, A equals C.
And this is the same thing actually. Yes, this is with the equality that you say with equality, but it's the same thing for the multiplication for other group. It's still associativity. What you associate, A, B or B, C, which is going first. But anyway, it doesn't matter. Just examples, some examples, right? So we have lots of restrictions, right? And we have this and opposite to this, right? So something that it is like this, it's true or it's not true. Okay. So if we take like some example of some axiom, each axiom divides our universe because it's a law, right? Divided to two places. Here it is like this, like for example, commutativity is confirmed here, and here it's not confirmed, right? So here it works, here it doesn't work. So each axiom is a restriction. We put the axiom, so we have only part of our universe which we see where this axiom actually works. The same thing is for actually definitions, because definitions, remember, are very close to axioms. We just define certain object that it's like this and not like that, right? We define it, so we define the area of the universe where these objects are located, right? So here, for example, one axiom works here, doesn't work here. Let's add another axiom. This is the first axiom. Let's add another axiom. For example, it divides like this, right? Again, here this axiom works, and here it doesn't work, right? So if we have two axioms, we have only this place where we see our objects. All the rest, some of the axiom does not work in other places. If we add more axioms, the area becomes even smaller. So like this, right? And like this. And we have very small area where this system of axiom actually works, right? So what this place that we call our, I may say, rational universe. So here, only here, we see something that have sense, some common sense. Here everything breaks. No laws, no nothing. Some of the laws work, some not. But here all our laws work. What kind of laws work in this part of universe? Just let's try to find out. Like first of all, remember it's logical axioms.
Yeah.
Logical axioms, right? They are formalized as mathematics, so it's part of mathematics. So mathematical logic. So logical axioms. There are quite a few of them. I didn't.
I have a question.
Yes, sure.
What's an unlogical axiom then?
What? Unlogical?
Yeah, what's an unlogical axiom?
Yeah, you may take any of the logical axiom, right? You take it opposition of it, right? Like something that doesn't work. I just suggest, like syllogism. Remember the syllogism? If A true, right, and this is true too, so B is true, right? So let's suggest that this doesn't work. So if A true and this is true, this is not true. This is total opposition to the axiom.
Okay.
So, and we can take it as a law too, by the way, why not? Or just don't think about any law. It may be true, this we can say. Maybe true, maybe not. Actually, so like the result?
geometry, or we build up the geometry using axioms.
Yeah.
Like the result may be questionable. So A is true, the hence if then thing, then operation, right? The then operation is true, but B is nobody knows. Maybe true, maybe not. Sometimes true, sometimes not. There's actually a field of such logic. It is called probability logic or fuzzy logic.
Oh yeah, fuzzy logic. I love fuzzy logic.
Okay, or fuzzy logic. So fuzzy logic is about that there's a certain probability for B to be true and certain probability that it's not true. But this is just, again, just a part, just one approach. But actually it may be some others. Yes? Yes.
A fuzzy logic is more specific than the logic you're talking about because the logic you're talking about is like it's if it's true or not. Fuzzy logic is like if it's true, yes, no, maybe, probably, more likely.
Yeah, there are quite a few variants of these logics. There are many other logics too. You can, again, as I said, you can get any of the axioms and take it opposite or to this axiom and talk about this, or you may just remove this axiom whatsoever, and you still have some logic, but already your logic will be very different from our logic that we actually use in normal current mathematics, current science, and everything. And that's pretty interesting thing. When we do that, we'll talk about it a little later. But for now, I just want to list certain axiom and laws that we use. Okay, first is like logical axioms, right? Then goes mathematical axioms. Modern math usually is based on the theory of sets, set theory. So there are certain axioms there too. So axioms of logic, there are quite a few of them. There are about 10 or 15, I forgot. Then set theory, again about 10 something. So pretty many axioms. Like, okay, now math, and then in our universe, what we have except logical and mathematical axioms? What do you think? What kind of restrictions we have in our universe?
Unlogical math. Unlogical.
Unlogical, we are not talking about it because it's something out of our world, looks like at least, right? It is not happening around us. Around us, so we see that the world is quite logical, right? And quite mathematical too. So
A geometrical axiom?
geometrical, it's still mathematical. Yes, geometrical, yes, but it's all in mathematics. Yes, you're true. You're true. Yeah.
Everyday common sense.
Everyday common sense.
Common sense. What common sense?
Everyday common sense.
Common sense, sort of, but common sense is, sometimes it works, sometimes it's not. So it's useful in one place, not another. So, but definitely what we have, like physical laws, right? Physical laws. In our universe, we have physical laws. All of what that we see obey these laws, right?
Yeah. Like,
Okay.
yeah,
Common sense, yes, in part. But okay, first of all, which is like mainly obeyed?
Wanna come and listen?
Society laws.
So what law?
Society, jurisdiction. Society laws, like a law. Like don't steal, or you will go to the jail, right? Society laws.
Political laws.
What?
Political laws.
Political, yeah, but again, they're very fuzzy, I would say, right? Yes, they are, but politics is pretty much dirty place where everything is broken. So, yeah.
Mama and Papa laws.
Mama, Papa laws, right. Right, so let's say common sense, but first of all, there are the, which are really important, morality laws.
Minority laws.
Morality.
What about the
So you should understand the difference between good and evil, right? So you should behave this way or not that way, right?
Oh, okay.
And then one of these important things is the laws of beauty. There are two laws too. Beauty laws.
Just absolutely shouldn't.
And this is field of art. This is field of music. This is field of poetry and literature actually too, partly, right? Because literature is about our life, so it's also include all these society laws, morality laws, common sense, and then goes more. There are more fuzzy, right? more fuzzy. But those are very pretty strict, actually, those laws. So this small area where we live, there's all these axioms and laws are obeyed in this part, right? Now let's talk about the other part of the universe. And this part looks like that nothing of this, so some of these are broken. It's different places, different parts of axioms and laws are broken. But how we deal with them, or should we deal with them? At least we live here. At first we should understand why we actually restrict, why we use all these things. What do you think? Why we use these laws? Why it happened that we have such amount of laws, axioms and everything? What do you think?
I think it's to keep law and order.
Okay, order, yeah. But why we need this order? What,
So like,
do we need this order at all?
so we learn how to behave.
Yes, okay. But why should we behave actually? What do you think? Can we behave like with what we want? We are free creatures, right? We are free, remember? Free. It's up to us. We can obey society laws or morality laws or even beauty laws. We can go ugly. Why we should not do that?
Because it's bad.
Yeah, bad. But what is bad?
Because if we do that, then we won't be living in the logical part. We will be living in the blocked part.
This is the block. What's block part?
Katya, you saying something? Say open.
No, like what I mean with Visa says, like, but when we have those rules, it's like people still don't follow them. There are some people
Yeah,
who speed.
we have lots of laws which we can break. Maybe it's difficult to break physical law, right? It's difficult to break, but who knows? Maybe nature breaks it somewhere. But well, for these laws, why we obey them actually, and why we use those laws too? What's the reason? The main reason for this? What do you think?
I don't know.
They make things better.
Okay, but why? Okay, better. It's a good idea to make things better, but why? Why should we make things better? Why they cannot go worse?
It helps us survive.
All right, sure. If the things go real worse, right? We can have banditism around, killing, wars, nuclear wars, right? Everything will just blown up. So this is all this is about survival. Survival.
That's what you said.
And not only these laws, but also physical laws. If you break physical laws, the physicists know, like for a pretty long time already, if the physical law is changed just a little, the whole our universe that we see will be so different that we, as creatures, we could not exist there at all. There would be no planet at all like Earth, no stars like Sun, and whatever. The whole thing will fall apart. We know that. That's about physical laws. The same is with mathematical axioms. They're even more deep than physical laws. Mathematical is about universe too. It's a very, very deep laws of the universe, and logic too. It's a very deep logical, very deep laws of the universe. So this is our area of survival. And that's why we use it. That's why we go with all these laws and obey them and learn them and search them and all that we do in mathematics and physics and everywhere and all science. Now let's talk about the other places, right? Definitely, if we are out there, we cannot survive in these places. Any of these laws broken, we would not survive here. It will be war or something much worse. The universe will explode. Something will happen and all this. And this is very, very, very narrow place where we can survive. But the question is, do we really care about this huge amount of things that we don't see them most of the time? Can we just don't care? Just we wouldn't care about all this? What do you think?
I think we still should care. We should be aware of actually what's going on.
Good.
If we just ignore the parts that aren't going on, we're going to be in a lot of trouble.
Yeah, maybe the enemy will come from there, right? We should be prepared, right? That's a good idea, right? Right. Better to be prepared. Better to know what is going on there across all these borders, right? To understand. Like right now, the virus came, right? If we knew that what virus will be coming, we'll be more prepared than now, right? With this COVID-19, right?
Yeah.
So this is all preparedness. That's a good thing. And there is another thing too. Again, just take a look at this. If we have like division, just one axiom, remember? One axiom. Division between two things, right? Between these two fields. Here axiom doesn't work, here it works. Does it look like something that we talk about? These two. Huh? Symmetry, right. It's opposition, definitely it is a symmetry. So if we have any axiom, actually it is a definition which defines you certain type of symmetry. Axiom works, axiom doesn't work. But as any symmetry here and here, right, they are different and they are in certain way similar, same, right. So something is preserved. So if we go with the axiom and it's okay, right, everything, still this axiom, we know that it has something from here where the axiom doesn't work.
But then that's a paradox because we don't use anything from there because then
Exactly, Vita, exactly. This is a symmetry and a paradox at the same time. So we understand here that the paradox actually is the behavior of our universe, which gives you symmetries, right? Which one side of the thing we see here and we work with it, right? But the other side always exists. It has similarity, right? They are connected together and they actually work together. But in this way, we see it from one side and we don't see it from another side. But they are always together like sides of the coin, right? Like one side of the coin and another side of the coin, right? They cannot go without each one. You see only one side, but yes, I'm listening.
Because if it was separated, it wouldn't be a coin anymore.
Pardon me?
If the opposite side was separated from each other, it wouldn't be a coin anymore.
Of course. If you separate, actually, it will be two coins, right? Again, two sides.
Yeah, I did that.
Divide this coin like this. There will be two coins, and each one with two sides. The same thing like with a magnet. Remember this magnet? Maybe you know, right? There's a north pole and south pole, right? If you cut magnet like this, what will happen?
There's two magnets.
Two magnets, right? Each one create two magnets. Again, the two poles, right? Again. And cut, whatever. The same thing with this thing. The same thing with the paradox. If we try to really cut it, not to take it as a whole and look from one side, but trying to cut it, we just create more paradoxes.
It's like what you said. The walls sort of connect the two, even though it blocks each other. They're like the walls in a room with me and Katya.
Right. This is connection, right? This is connection. This is actually the connection is the coin. So this is just the side. What we see is just one side of the coin. The other side is what we don't see. But the actual coin is this. So the paradox mainly it explains and describes the whole thing as it is, the thing with two sides. And we usually see just one side. This, or we may see another side too. There's this called the change of the frame of reference. If we can go from the other side of the coin. That's very difficult maybe to do in the universe. There's significant material things to do, and we usually don't know even how to do it most of the times. But it's always can be done. Okay? Any questions on this? No?
No.
Okay. So we see about the axioms and everything, right? Now, just a short thing about symmetry. We have a face, right? And we have eyes, nose, right?
A mouth.
Mouth, right?
A mustache.
Mustache, right? And then hands, right? Legs, whatever. And you see that it's symmetrical, right? Pretty good symmetrical, right? Reflection symmetry. And there are many other symmetries here. If you go further, like if you look at your fingerprint, right?
Symmetrical.
It goes like this, right? Your fingerprint. It's a definitely symmetry of a high level, and many other symmetries. So the symmetry actually is the main part of a beauty.
It is?
Yes, it is. This is beauty. If you have like your face not symmetrical, like no eye, This is ugly, right?
Oh,
Or
you
you
see your
or you
friend.
cut your nose. The half nose is cut, right? So you have only that kind. Or no ear. This is all ugly, right? No hand, right? And all that sort of thing. So you just change the symmetry or break the symmetry, and you will come from beauty to ugly. So it's the whole thing. So symmetry is a main thing of art. The same thing in music. There are certain harmony between notes. Remember I told you, right? So certain relation between them, it gives you harmony. Or in other words, consonants. And consonants is where the frequencies of these sounds have relations like 1 to 2 to 3 to 4, but not like 1 to like 2.5, right?
Yeah.
So this is called dissonance. So this sounds ugly.
Ugly?
Yeah, a little ugly, yeah. Dissonances. But dissonances are used too as oppositions to the harmony. In the music, there goes like consonance, dissonance, and all that sort of thing. So the music goes like, you know, like that. Beautiful patterns. But anyway, there are laws in these patterns too. There are lots of laws. Poetry, again, like a rhyme, right? The rhythm, of course, like прекрасное далеко, не будь ко мне жестоко, right? Three, the rhythm goes. The rhyme, далеко, жестоко. Далеко, жестоко, it's a rhyme. So it's a symmetry again. So symmetry is the main part of the beauty too, beauty laws. Now let's talk about one approach. Okay, we have these amounts of axioms, but we now understand that axioms actually and all kind of definitions, they actually describe our universe from one side. Each axiom from one side, and the area of our knowledge is going very, very narrow, right? But there is another part, like an iceberg, which is unseen, where many of these axioms are broken, right? And this unseen part of iceberg still is very significant to the whole thing that we actually use and we live with, right? Like iceberg, just 1/10 of iceberg is outside, like, and the main thing is under the water, right?
Yeah.
So, and to understand the behavior of iceberg, we have to know what is going on there. So the same thing as in the previous picture, right? So we need something else, not only these laws and axioms, but something else. So we need to take into consideration oppositions to these laws and the places where these laws and axioms are broken. Sometimes maybe to use them, but mostly because it's evil use, mostly because just to know where the evil will come, like Katya said, it's correct, to be prevented and to know how to deal with all of this. And on this way is started by the guys, remember these guys who created non-Euclidean geometry. It's Riemann and Riemann, Lobachevsky, it's Russian, Lobachevsky, and some others. Then I told you about David Hilbert, who actually tried to create different types of geometry by using oppositions to the geometrical axioms, right? So step by step, scientists are coming to describing all this, but there's always a question: why can we not go with something that does not have any of these axioms, and then just go step by step, adding by axioms, look what is going on? Just start from something that has none of these axioms. And how we can do it? We can start from one very significant paradox, which is heavily used in mathematics and everywhere, in linguistics, everywhere. And this paradox is called symbolism.
Symbolism?
Symbolism, yes. It seems like a very simple thing that everybody knows. Symbolism is about that you can take anything in our universe any, and substitute it by,
Substitute it?
substitute means use something else by anything else
Holes.
as a representation of this.
Yes.
So for example, there are real things like a war, right? Coming war, people killing each other, fighting, right? And then we go to the theater, and then on the stage, some people, actors, right? They represent, or they play, right? They play as if they are fighting, they are like killing, they representing dead people, whatever, all these problems between people, everything. This is representation of play, this is substitution. So these actors, they're substitute real people in the real story, real war story. And also they represent not only people, which is called symbol. So any actor become a symbol of real guy, real like war hero, right? And maybe this is a traitor, war traitor, right? This guy represent this, and this represent this. Like for example. But they represent not only people, they represent their relations, right? So this he actually he behave. What's the word for this? What traitor do?
Betray.
Huh?
Betray.
Betray, right? So he betray a hero, right? For example, right? And hero tried to save traitor, but he betrayed him, right? So against in the play, this guy he play like he's caring about this guy, and this guy like behave like he's betraying this guy, but they're not really betraying or loving each other or whatever, right? They're just playing. But their relations actually, there's not only people substitute each other, but also relation substitutes the real relation. Relations in the theater, in the play, are substituted by the real relations. And this is called, remember this word, mathematical word, this is called isomorphism.
Isomorphism?
Oh, isomorphism, yes. When not only, this is strictly connected with symbolism, so not only symbol represent something else in the universe, but also the relations between A and B, relations, okay, are also represented. So A prime, relation prime, and B prime. All three. A is represented by A prime, B is represented by B prime, and relations. This relation is represented by this relation.
Relation prime, that's so dirty.
Yeah, relation prime, yes. This is called isomorphism. Not only symbolical representation of real guys by actors, but also their relation is represented too.
Yeah?
Yes.
So would say isomorphism is a pretending to be something you're not.
Yes, somehow, yes. But interesting thing is that in symbolism, what is the paradox in this? That actually it was found out, and you can think about it. It's a very, very nice thing to think about it. That actually any A in the universe can be represented by any B in the universe. That's a very interesting thing. Very different stuff. Like this is like a galaxy, right? And this is like maybe an ant, right? Or maybe some small bug, right? And the small bug can represent a galaxy. In a certain case, if you're smart enough, you have enough fantasy, you will see that it can be represented. The same thing like actors play, the bug can represent maybe for example quantum. Something that we don't even know what is exactly this. But why not? Bug can. It's not that difficult for him. Difficult maybe to us. So, and when you look at this, the whole idea of symbolism is becoming very paradoxical, because what the hell is happening in this universe? You know, anything can be represented by anything else. Why? If it's represented, it is a symmetry, right? Remember?
Yeah.
So anything in the universe has some similarity with the other thing, whatever, but they have similarities. That's why we can count. Remember? We can count galaxies. We can count this and this and this. Remember? That's why we have this what we called universalia. The common things that we have for any A and any B, we have certain relations. Remember this relations between past, remember past, present, and future. Remember quaternions I, J, and K. So if you have something, for example, we're talking about time, right?
Yeah.
We take time. And we have this thing. This past goes to the present, transforms into the present,
Present goes to the future.
present to the future, right? And
And then
also
the
and
future
also
goes
we
to the
have
past.
this, right? Which we have life, right? So but past transformed to the future. And remember,
Question.
yeah, question.
Can the future also go to the past?
Future go to the past? What do you think? If you take life back, like this. So
Yeah,
anti-time,
yeah.
yes, it will go.
For example, yesterday, today was tomorrow. Let's say yesterday was 3 a.m. Today would be 3 a.m.
I agree. This is circular. Future becomes past in the next circle. Yes, it's true. Mhm. So this is do you notice actually that yes, exactly. Future goes to the past. Yes.
Which is ironic.
Yeah, interesting. But well, so this is about time. Like we see in time, right? In thing that we call time, we have these relations. And remember, we actually denoted them like I, J, and K. Remember?
Yeah.
Yeah.
Those are quaternion units, quaternions, I, J, and K. But if we talk, okay, we talk like about life. But for example, let's take market relations. So sell, buy, whatever, right? We have some product. We have some product, right? And we sell it in the market and get some money, right? And then we go and buy something, and we got product 2. So product 1, product 2, right? And we can repeat it again and again. If we repeat, right, we have the circle, the same thing. So we have this vector, product 1 to product 2. The simplest market before the money was invented was like exchange, product 1 to product 2. You go, I have a chicken, you have maybe some beautiful stone, right? And I come, I say, oh, I like your stone, let's exchange, right? I give you chicken, you give me stone. Okay, that's done. This is simple market, right? But now we have money in the middle. So the same thing like here. We had life, and we can do not divide it before, but then we see, okay, there's past, there's present, there's future. So there are 3 elements in our life, in time, right? We have the same 3 elements in product. So we have market, right? And market goes product, money, product. Again, I, J, K. What is this? This is what we were talking about before. Isomorphism. So time and market are very different things, and still are very same, and they have these relations. If you go deeper, you will see that actually anything you can imagine in this world, you can whatever. They have this thing. They have these relations I, J, and K, and they circle and circle and circle and circle. So it's very similar, and it's very impressive that these simple things, and these are mathematical things, right? Remember, there's quaternions, mathematical objects. So they are applicable to anything in the universe. So they can represent this I, J, and K can represent anything you see around. And this is, if you have questions, ask, because I have questions for you after that. Okay.
You don't have any questions?
Huh?
You don't have any questions?
No question. Okay, guys. So then my questions then.
Homework?
Yeah, homework.
Uh,
Homework?
write it somewhere. Okay, guys. Okay. So the first question is.
Wait,
Yeah, sure.
wait, please. Okay, go ahead.
Okay, give 3 examples of your own for I, J, K around you. For three different things that you can find around you. Any, whatever you find.
Give 3 examples of your own of 3 different things in a relationship.
And their relations is like I, J, and K. Just like this, whatever, give, put all your fantasy into it. Whatever you can find, and play with them. If you can find more, will be great. Okay. Second, the question is, what kind of rotation symmetries make these multiple multiplications by, like 1 multiplied by I, okay, then again by I, then again by I, again by I, okay? What kind of rotation symmetry it is?
What? Say it again?
You have 1, right? Okay, I will maybe. These I, J, and K are vectors, remember? So we can do this thing. This is vector 1, right? This is vector I, right? This is vector J, and this is vector K. And if you multiply 1 by I, then again by I, then again by I, then again, something happens. It's called rotation, actually. Just to give you a clue. And what kind of rotations will happen in this 4-dimensional space? Just look at it. There's 4 dimensions. 1, I, J, K.
What do you mean?
Yeah, I don't understand the question.
You have 1. Okay, another clue. You have 1 multiplied by I.
You get I.
You get I. Where is I?
It's perpendicular.
Yeah.
Okay.
This rotation.
Yeah.
So just describe this, look at this, right? Then the same thing for J and K. What kind of rotations are those? Just look at these things. And then think what is going on with 1, right? Just for example. So this is the second question. Just think about it and look what kind of rotation. And now the third is, now when you talk and you thought about these rotations, how they work, right? Just what interpretation of this rotation, of these rotations, are in your examples. You have examples on your own, right? And what these rotations interpret, what the rotations symbolize, what kind of relations in these things they symbolize. In your examples, your own examples, not my examples. You can think about my examples too. I know time, market, but. And this geometrical actual interpretation too. This is geometrical, right? Geometrical 4-dimensional. But you think about your examples and what these multiplications by I, by J, by K, what they actually represent. Okay?
Okay.
Okay. No questions? Any questions?
This one was interesting. Thank you.
Okay. Thank you, guys. Okay, then. So that's it, right? So, okay. See you next time then. See you guys.